Welcome, and we were discussing about the speed control of three-phase induction motor, of which earlier days people used to adopt different methods. For example, if it is a wound rotor induction motor, you can vary the speed by varying the rotor resistance, or you could vary the supply voltage alone. That is, you can only reduce the supply voltage from its rated value. Then also speed control is possible, but over a very limited range. And also if you adopt voltage control method, the pull out or maximum torque decrease drastically. And then there are methods also adopted in earlier days, that is you can control the speed of the induction motor, and they were very popular in those days. That is, you have two sets of say stator windings. One set will give you suppose 4 pole, other windings will not be used, or other winding when it is used it gives you 2 poles, and thereby you can get synchronous speeds of 2 values. Apart from that, of course, same winding can be used to create different number of poles in the ratio of 2, and you could control the speed of the induction motor. Another interesting method was that I just mentioned. If time permits, I will discuss. That is, you can control the speed of a induction motor, but in this case, in this particular method, you do require 2 induction motors. One of them must be a slip ring type. So, what you do, you supply the first you take the wound rotor induction motor, supply the stator of that induction motor with rated voltage frequency, and then through the secondary, that is the wound rotor type induction motor rotor terminals, you will get induced voltage of slip frequency, and then that voltage is used to energize the second induction motor, which is cage type, and these 2 motors must be coupled, and then you can get some 4 number of discrete speeds. One is corresponding to P1 pole machine, 2f by P1, another is 2f by P2, another is 2f by P1 plus P2, another is 2f by P1 minus P2. And so, this was the thing, but I will just tell you qualitatively how this scenario has changed to control the speed of the induction motor, because the speed after all is decided by the synchronous speed of the rotating field, which is nothing but 2f by p. So, in earlier days people were thinking about changing the number of poles, but nowadays what they do, they try to change the frequency of the supply, thereby changing the synchronous speed, hence the speed of the rotor of the motor. Now, the change in frequency is not very straightforward, but it is like this. The block diagram I draw, that is, you have got 3-phase supply here, 3-phase supply, and then you have got a 3-phase inverter. No, first you have a rectifier, a rectifier. Make this supply DC, it is rectifier, maybe diode bridge rectifier, and this is your 3-phase supply A, B, C or R, Y, B. Now, here you get DC, and then this DC is fed to a 3-phase inverter, 3-phase inverter. Inverter, as you know, changes your DC supply to a 3-phase supply, balanced 3-phase supply. of frequencies decided by the strategy you adopt in this inverter control circuit, that is frequency of this output of the inverter voltage, both frequency as well as the magnitude of the voltage can be changed. The idea is like this. So, you will have two control, one control one control for voltage, maybe another control maybe for frequency, and you at the output of the inverter, it looks like you can generate any given voltage at any given frequency. Now, this one is used to supply the stator winding of the induction motor. The point in my last class I was trying to tell, the applied voltage to the motor per phase, if it is V1 RMS value, this we know it is 4.44 F flux per pole into kW 1 into N1. Now, this equation is interesting to note that this is 4.44 F kW into N1 into F. Now, this ratio look at other things being constant of the machine, I cannot do anything, and this is flux per pole, and the value of the flux per pole will be rated value if you apply rated voltage and rated frequency. What is rated voltage and rated frequency? That is the nameplate rating of the induction machine. Therefore, that is called the rated flux. Therefore, I must say that in order to control the speed of this induction motor, if you vary the frequency downwards, that is 50 hertz motor, I will vary the frequency to 45 hertz, 40 hertz, and will get different synchronous speeds, and I know that that will be the speed of the rotating field, and therefore, rotor cannot but run as dictated by the synchronous speed of the machine, very close to synchronous speed, but below it with some small value of slip. Now, the question is, if you keep the voltage fixed and go on decreasing the frequency, what happens is this flux will rise, and to develop that flux you will require more and more magnetizing current. And the BH curve tells me that if you reduce the frequency, keeping the voltage constant, the machine may go into saturation, because BH curve of the material after all is of this kind, and the rated flux is at the generally at the knee point of the magnetic circuit. So, as you change the, and this is the magnetizing current, as you reduce the frequency alone, the if you make the frequency half, you know, flux will be doubled and current drawn will be very large, maybe many times more than the rated current even of the induction motor, and then we say saturation has taken place. Therefore, machine should not be worked in saturated condition, it unnecessarily draws very heavy magnetizing current. In any case, if the machine is supplied with some protection, even under no load condition, it will draw very large magnetizing current, fuse will protect the motor, that is the idea. Therefore, if you want to vary the frequency from its rated value and you want to decrease it in order to run it at lower and lower speed, there is a problem now. So, the constraint is or the if you want to reduce the frequency, also reduce the supply voltage, that is this voltage and this frequency. Also reduce the supply voltage supply to motor, supply voltage to motor, such that this V by F ratio, this ratio remains constant, then at least you are sure machine will never go to saturation. Okay? And not only that, rated flux will be preserved. Suppose the machine rated voltage is 440 volt and 50 hertz. If you want to run the machine and suppose P equal to 4, to give you concrete example, the speed of this machine when it is supplied like this, it will be close to NR will be close to and less than 1500 RPM. Okay. Now, what I will do? I will apply 220 volt, 25 watts, so that the ratio once again remains same as 2, but the synchronous speed, because it depends only on frequency and number of poles of the machine, it has become half. So, new rotor speed will be less than and close to 750 RPM. That is the idea. And this is true for any lower frequency. As you decrease the frequency, speed can be. Therefore, this control, of course, I have shown independently. You can make logic this that, so that you sense supply voltage and frequency such that the V by F ratio remains constant. Okay, understood. So, the idea is this, that is, you apply the voltage, variable frequency. It is often called variable voltage, variable frequency control. Now, the question is what about the torque slip characteristics under this condition? If you recall, we can easily do it for from the very involved equivalent circuit, but let us try to get the idea from this equation, just to get a first hand experience how the speed will change. So, we know this is the expression of the torque if all stator impedances neglected. All stator impedances neglected. And mind you, what is the value of K? K was some 3 V1 square by 4 pi ns, most probably like this, x2 dashed, K, the constant value. And also we noted that T max was equal to K by 2. Now, this was the thing, most probably T max. Now, you see, in the denominator of this expression of Q, who decides the value of T max, there is Ns. This Ns can be written as 2f by P, is not this Ns. And similarly, this x2 dashed can be expanded as omega into L, leakage inductance. So, it will give you another F here, Therefore, you see T max is proportional to V 1 by F whole squared. It will be proportional like that. Therefore, since I am varying the frequency in the downward direction and also maintaining this V by F ratio constant, I am maintaining. Therefore, it looks like T max will remain practically constant, if V 1 by F is constant. Okay. So, what happens to the torque slip characteristics? Now, look at it, very interesting. What I do, only thing is this time, since I am varying the frequency, it is easier to rather sketch torque speed characteristics instead of torque slip characteristics. Why? It will be clear. Suppose this is the thing. This axis I called speed axis, speed, okay, and this is suppose the torque slip characteristics of the induction machine with V1 rated and F rated, these characteristics, and this is the synchronous speed NS rated. This is suppose the torque slip characteristics, electromagnetic torque developed, and rotor speed will be close to this one, that is all. Now, suppose you change the voltage to half and frequency also to half. Therefore, news NS1 therefore was NS1, if you call it is rated NS1 was equal to 2 F rated by P, and this is NS1. Now, if I reduce the frequency by half and voltage also by half, the new synchronous speed NS2 will be NS1 by 2, NS1 by 2. Therefore, let us see what will happen to that torque slip characteristics when you have reduced both the supply voltage magnitude as well as frequency to half compared to its nominal values or rated values. Then it will be NS2, which is equal to NS by 1. Will the T max change? No, it looks like T max will remain same. Therefore, I draw a dotted line here, and it is expected that the torque slip characteristics will be also like this approximately. Only thing is this slip, of course, I am not plotting slip, this might change a bit, okay. But anyway, this torque slip characteristics will come like this. Therefore, when you reduce the frequency, you can draw then y at half for various values of frequencies. You can draw the torque slip characteristics. So, machine will run at NS1 at this speed, a very smooth control of induction motor speed will be possible. Are you getting a number of characteristics I have drawn? B by constant, F decreasing. It can be nicely drawn, but anyway, this is the idea. Okay. Now, what happens? This is an equivalent equations I have banked upon is these equations. What happens if there is R1, X1, magnetizing current, all these things are present? Oh, in that case, what will happen is this T max will decrease as you decrease the frequencies a bit. For example, one characteristics will be like this. The next one, synchronous speed is different, its value will not really remain same, it will become less because of extra drop in R1 X1, because Thevenin's voltage and supply voltage there will be a small difference, the drop in R1 X1, and it will be another will be there. So, at lower speed the peak value in fact will never be equal to the peak value of the torque corresponding to nominal values of voltage and frequency. So, it will be something like this here. So, NS1, NS2 and so on. In fact, you can run it down to very low speed. Load torque is supposed like this, then machine will run at this speed, at this speed, at this speed, at this speed. So, same load torque can be supplied at lower and lower RPM. So, you must understand that instead of drawing slip will be different in different frequencies, Ns minus Nr by Ns. So, that will be somewhat confusing. It is better you draw absolute values of speed and torque. So, a smooth control of speed is possible in this way. Now, the question is, so this is in this curve I write it that f decreasing because of some practical limitations. You cannot go maybe frequency less than 10 hertz, okay, that is because the drop in R1 X1 will be too large for that current. But nonetheless, you can go down to very low speed over a wide range, that is you vary it will run. Will it incur extra loss? No, not at all. Assume there will be some switch losses in the inverter, but that is much smaller compared to rotor resistance starter, where you kept the rotor resistance when the machine was supplying load. Acha. Now, the question is, so this T max will decrease a bit because of because these equations are only true if you neglect all stator impedance. Anyway, that can be done. Now, the question is, what happens? Can I run this induction motor higher than its rated speed? The answer is yes, by varying frequency, because frequency can go down from its nominal value, rated value, or you can make it also high. For example, 50 hertz motor, I will supply it from 55 hertz, synchronous speed will increase, or say 60 hertz, because my inverter block will provide me that kind of frequency variation, no problem. Therefore, if you increase the frequency, then how this torque slip characteristics will be changing. Achha, before I discuss, suppose I want to also increase the frequency, so that I want to run it, because in DC motor control, you can control the speed below the rated speed by controlling armature voltage. Similarly, you can control the speed of the DC motor at higher values by controlling the field current. Therefore, it may be necessary to control the speed both down and up about the rated speed of the motor. In that case, what should be the strategy? Look at this equation. Now, I am telling, I will write it here. Now, we know this was most important thing, deciding factor, that is phi is proportional to applied voltage by frequency. Now, what I am telling, I will increase the frequency from its rated frequency, f rated. 50 hertz, I will make it 60 hertz, like that. Now, you see in this equation, and V 1 is what? Corresponding to, suppose V 1 is rated. I know by this time that if you decrease the frequency, your numerator V 1 must be reduced by same proportion, otherwise saturation will take place. But in the other case, if you want to increase the frequency, the saturation problem will not be there, because if you fix, one must understand that if you apply 60 hertz, should I apply a voltage which will be 6 by 5 into V 1 rated? No, that is what I want to say, because the winding has got a rated voltage, based on that the insulation has been provided in the machine. Therefore, when we talk about increasing the supply frequency in order to run the induction motor at higher than its rated speed, then it is obvious I cannot touch V 1 rated, it is already V 1 rated, say 400 volt machine, 440 volt machine. Although I will increase frequency, but I will not touch V 1 rated, then it will, machine will be stressed. Rated voltage above rated voltage I should not apply, that is the rule. Therefore, V 1 rated in this case will be fixed. Then you talk about increasing the frequency, because then flux will go on decreasing and so on. Now, the question is how the torque slip characteristics then look like. Go by this equation once again qualitatively, let us see. Now, what I am doing, I am keeping this this T max roughly proportional to, we have seen V 1 by F whole square. Now, what I am telling, in this particular case it is inversely proportional to F square, because V 1 rated is fixed. Therefore, the peak value of this torque will reduce drastically as you go on increasing frequencies. However, the synchronous speed will go on increasing, because synchronous speed has nothing to do with voltage, Ns equal to 2f by p. You have increased the frequency, synchronous speed will increase. So, if I draw a vertical line here, this is the f decreasing, keeping V by F constant, this zone. In this zone, I will increase the frequency, keeping the rated voltage applied to the machine constant. Okay. Because you know, if you increase frequency, keep rated voltage, physically also we can say flux per pole decreases, therefore, torque must decrease. Although equations are there to support me, but anyway that way also you think, you are decreasing the frequency. Therefore, it will, so how the torque slip characteristics will look like? Your synchronous speed will increase, with respect to this rated voltage, it will be like this. Then you want to, I am sorry, I should draw it here, NS1, NS2, NS3 it was, it is some NS1 higher speed H, NS2 higher speed. So this will be like this. What I want to tell, this will decrease quite fast. You forgive me for this. Higher speed, the peak value will go on decreasing, because inversely proportional to frequency. Therefore, we see that if you want to control the speed of the induction motor, the elegant way to do it is control the supply frequency. Do not start talking about I will change the number of poles, because nowadays very nice inverters are available and you can vary the frequency. The moment the variation of frequency comes, two questions must be answered. Suppose at rated voltage, rated frequency machine is operating, start from that point, that decides the rated flux. if I decrease the frequency in order to run the machine below synchronous operating speed, nominal speed, I must decrease the frequency, but while decreasing frequency it will be suicidal if you keep the voltage at its rated value, because of the fact saturation will take place, it will demand much and higher magnetizing current, all the problems of saturation will come in. Therefore, while decreasing frequency, voltage applied must be also proportionately reduced, such that T max will remain constant, and at various synchronous speed the characteristics you can draw, put the load torque characteristics, point of intersections will give you the speed over a wide range down to a very low speed. You can control the speed of the machine. Can I control the speed of the induction motor above the rated speed? Yes, you can, by increasing the supply frequency. Should I once again then increase the applied voltage in the same proportion so as to get same flux? No, there is a restriction. Supply voltage applied to the machine should not be exceeded from its rated value. Therefore, while running the speed at higher than its operating speed, you must make sure V 1 applied, this is rated condition torque slip, V 1 applied is held fixed, increase the frequency, then the torque slip characteristics will be like this. Therefore, it is just like this portion is called actually flux control. Compared to DC machine, if you see, okay, you are essentially keeping V fixed, F increasing. If you do F increasing, flux you are decreasing, flux per pole. Like in the higher speed, if you want to run a DC motor from its rated value, you have to decrease the field current, flux in the machine is reduced. So, all these things now come out very nicely, that you can also control the speed of the induction motor over a wide range. Thank you, we will continue.